What if I told you that some of the smartest people on the planet still can't agree on what reality even is? That's not a joke, it's physics. Welcome to the bizarre, mind-bending world of quantum mechanics, where logic breaks down, particles behave like waves, and reality depends on whether or not you're looking at it. Today we're exploring 10 real quantum theories so strange that even scientists can't reach a consensus. What if every decision you make creates another version of you living in a completely different universe? The many worlds interpretation was first introduced by physicist Hugh Everett in 1957. It suggests that every time a quantum event happens, like an electron choosing between two paths, the universe splits. One version takes one outcome, and another version takes the opposite. Both are equally real, just in separate branches of reality. According to this view, there isn't just one timeline. There are infinite timelines branching off constantly. There's a version of you that hit snooze this morning. That's this one in reality, and another that just didn't. The math checks out, but the idea that trillions of new universes appear every second makes some scientists uneasy. What if every particle in the universe follows an invisible current guiding it through space? Louis de Broglie came up with the idea in the 1920s, and David Bohm later developed it into what we now call the pilot wave theory. In this view, particles, like electrons, don't randomly jump around. They have definite positions and paths steered by an unseen pilot wave. It's like there's a secret ocean of waves underneath reality guiding everything that moves. The theory restores a sense of order to quantum chaos, turning randomness into hidden determinism. But there is a catch. It means everything in the universe is connected instantly, no matter how far apart. This non-locality conflicts with Einstein's theory of relativity, which says nothing travels faster than light. Despite that, pilot wave theory predicts all the same experimental results as standard quantum mechanics. It just gives a completely different explanation for why. Some physicists love that idea, others think it's too conspiratorial, like the universe is rigged behind the scenes. What if your own thoughts decide what reality becomes? In the 1960s, Nobel Prize-winning physicist Eugene Wigner suggested something radical. He proposed that consciousness itself collapses the quantum wave function. In other words, until a conscious being observes a system, it stays in a blur of possibilities. Once it's observed, the system picks a single outcome. Reality then locks in. This is known as the observer effect, and it's one of the most controversial ideas in all of physics. It takes quantum weirdness and ties it directly to the human mind. The famous thought experiment, Wigner's Friend, highlights the problem. If a scientist measures a particle in a closed lab, that scientist sees a definite result. But to someone outside of the lab, the scientist and the particle are still in a superposition. Both possibilities at once. So whose observation actually decides reality? Most modern physicists don't buy into the idea that consciousness has special powers, but no one has fully disproved it either. What if the force of gravity is secretly deciding when the quantum world becomes real? Physicist Roger Penrose, who later won the Nobel Prize, proposed that gravity could cause quantum wave functions to collapse. When a particle or object becomes massive enough, the curvature of space-time itself forces it to pick a state. In other words, small things like electrons can exist in multiple places at once, but as objects get heavier, gravity prevents that superposition from holding. Reality snaps into one version. This idea tries to connect the two biggest theories in physics, quantum mechanics and general relativity. The problem is, it's incredibly hard to test. We'd have to create a superposition involving a relatively heavy object, which current technology can barely manage. Still, experiments are underway with tiny mechanical systems to see if Penrose's idea holds up. If it ever does, it might finally bridge the gap between quantum physics and Einstein's gravity. What happens when someone watches another person watching quantum reality? The Wigner's Friend experiment sounds simple, simple, but leads to mind-bending consequences. Imagine a scientist's friend inside a lab measuring a quantum particle. For the friend, the measurement collapses the wave function. But for Wigner standing outside, the entire lab, including the friend, are still in superposition until he opens the door and looks. So, which moment counts as the real collapse? The friend's observation or Wigner's? Recent experiments have even tried versions of this scenario using entangled photons and automated detectors, hinting that reality might depend on who you ask. It exposes a deep flaw in our understanding. If reality depends on observers and observers depend on reality, the whole framework becomes circular. The paradox remains unsolved and continues to spark debate about whether objectivity in physics is even possible. What if reality just collapses on its own without anyone watching? In 1986, three physicists, Girardi, Rimini, and Weber, proposed that the wave function spontaneously collapses at random times. This became known as the GRW theory. They suggested that every particle in the universe has a tiny chance of collapsing into a definite state every second. For one particle, that's almost never, but for large objects made of billions of particles, collapses happen constantly. That's why the macroscopic world looks stable while the microscopic world looks fuzzy. This theory makes the weirdness of quantum mechanics a natural part of physics, not something triggered by observation or consciousness. The big question is whether we can detect these spontaneous collapses. So far, experiments haven't found solid evidence, but the theory remains one of the most mathematically clear attempts to fix the measurement problem. What if reality doesn't change when you measure it? Only your belief about it does. Cubism, short for quantum Bayesianism, flips the whole quantum puzzle on its head. It argues that the wave function isn't real at all. Instead, it represents your personal expectations or beliefs about what might happen when you make a measurement. When you see an outcome, you simply update those beliefs, just like someone updating their odds in a game of poker. The universe isn't random. You just don't know enough. This makes quantum mechanics less about reality itself and more about information. It removes the mystery of collapse entirely by saying the wave function was never physical to begin with. What if measuring one property of a particle changes the outcome of another, even when they seem unrelated? In 1967, physicist Simon Kochen and Ernst Specker proved something shocking. You can't assign fixed, pre-existing values to all properties of a quantum particle. The result of any measurement depends on what other measurements you choose to make alongside it. This is called contextuality. It means that in quantum physics, the context of an experiment literally changes the reality you find. The act of measurement doesn't just reveal information, it creates it. This theorem killed the dream of building a classical hidden variable model where every property existed before we looked. What if nothing in the universe exists on its own, only in relation to something else? Carlo Rovelli, an Italian theoretical physicist, introduced relational quantum mechanics in the 1990s. His idea is that properties like position or spin don't exist absolutely. They only exist relative to an observer or another system. For example, an electron's spin might be up relative to one measuring device, but down relative to another. Both are valid within their own relationship, and there's no single universal reality that overrides them. This model elegantly sidesteps the observer problem by saying every observation is true from its own point of view. What if the quantum multiverse and the cosmological multiverse are actually the same thing? The all possible worlds theory is a modern attempt to unite quantum physics with cosmology. It suggests that the branching worlds from quantum mechanics and the many universes predicted by cosmological models are two faces of the same coin. According to this idea, every possible history that could exist, from galaxies forming differently to atoms vibrating in another way, does exist. Quantum physics just describes our limited view within that infinite cosmic web. It's an elegant solution for some theorists because it explains why the universe seems so perfectly tuned for life. We just happen to exist in one of the countless branches where conditions allow it. Critics call it untestable, which in science is a big problem, but its defenders say it could one day link quantum theory with the large-scale structure of the universe. All right, guys, that has been our list for today. Thanks so much for checking it out. I've been your host today, Olivia Kozlowski, and I'll see you again soon. Goodbye.